All right, active transport, it is selective. So the protein channel only moves the one thing. So if it's a sodium channel, it moves sodium. If it's a sodium-potassium channel, it moves sodium out and potassium in. So channels can go two ways. There's also cases where sodium comes in and glucose comes in. Though that will be secondary active transport. We'll talk about that in just a second. So ion channels can go one way or the other, or we can have things swapping, or we can have two things moving at the same time. Most commonly studied is the sodium-potassium pump. I'll show you that in just a second. And let me make this little point real quick. Before we get too much further. If an ion channel opens for any reason, if these open for any reason, those ions move immediately with the So if it's a gated channel and it opens, sodium moves right away. And then if we want sodium to get out, we're going to have to pump it out. It's going to have to be the option. And then we're going to have to use ATP. All right, a little animation. And if sometimes your computer's weird about a whole virus thing. So if you're not able to actually use this, I do have an animation from McGraw-Hill with a link that you can go to. It's just different than this, but it's the same idea. So here we have a phospholipid membrane. Here we have these little purple balls. Purple balls are going to be polar. There's no way to get across except through a protein. And so the cell wants these purple balls inside. So here's our protein. Has a particular shape. Look at our little binding site. Notice that that binding site, if you can see that, doesn't look the same as the purple ball. It won't fit it. So, click on a step. There we go. Here comes ATP. See, that third phosphate broke off, bound to the protein. The protein changed shape. Now it's the same shape as the purple ball. So then when the purple ball drifts in and binds to the protein, whoa, the protein's going to change shape. And it opens. And then the phosphate pops away. It goes back to its original shape, which means the purple ball had to let go.
What is the purple ball?
An ion.
An ion, okay.
Yeah, just something polar. So we'll say an ion, probably. It has to be the loop. And then it just keeps going. So you can see how just that protein just keeps changing shape as things bind to it. So there's a way that ATP is being used where it changes the shape of the protein channel. So the sodium-potassium pump, again, most commonly studied, and have a little active GIF going on here. Notice that ATP is being used to change the shape of the protein. Now we have sodium being thrown out, two potassiums come in, potassiums can bind. When they bind, it changes shape. ATP lets go, it closes, potassiums go back in. So that's going to be running continuously. This one is showing you, first of all, I want you to look at the way the artist is conveying concentration. Sometimes an artist will convey concentration by putting the actual concentration next to it, the amount, millimoles, millimole out. And in this case, the artist chose to make sodium big and bold, and that means there's more sodium outside the cell, and then the sodium in here is smaller and not bold. So there's less sodium on the inside of the cell. So just understand what that's showing you. More potassium inside the cell, more sodium outside the cell, and it's the sodium-potassium pump that keeps it going. Keeps it that way.